Have you ever watched an old mechanic pop the hood, listen for about 10 seconds, make one small adjustment, and suddenly have the engine running perfectly? No scan tool, no laptop, no expensive diagnostic equipment, just knowledge, intuition, and a set of techniques that quietly disappeared between one generation and the next. Today we're counting down 20 genius engine tuning hacks that only the old mechanics knew. These are the tricks that kept cars running beautifully for decades. Stick around, like the video, and subscribe so you don't miss a single one. Number 20. Reading spark plugs like a book. Pull a spark plug from any engine that's been running a while, hold it up to the light, and an old mechanic could tell you exactly what was happening inside that combustion chamber. Not approximately. Exactly. The color, the deposits, the condition of the electrode, it all told a story that no modern sensor can fully replicate. A perfectly tuned engine produces a spark plug that looks light tan or grayish. That's the sweet spot. If the plug is bone white or blistered, the mixture is too lean, and you're risking serious heat damage to the internals. If it's black and sooty, the mixture is too rich. Carbon deposits build up, efficiency drops, and eventually you've got a fouled plug that won't fire properly. Old mechanics didn't just glance at the plugs and move on. They read each cylinder individually. One fouled plug, while the rest looked perfect, pointed directly to a leaking valve, a bad injector, or a compression issue in that specific cylinder. It was a targeted diagnostic, performed with nothing more than a sharp eye and decades of pattern recognition. Modern mechanics call it primitive. Old mechanics called it accurate. Number 19. Vacuum advance tuning. Most people who work on older engines know about mechanical timing advance. Fewer understand vacuum advance. And almost nobody outside of the old guard understood how to tune both together to get the absolute best performance out of a carburetor engine. The vacuum advance unit connects to the distributor and responds to engine load. Under light throttle, when manifold vacuum is high, the vacuum advance pulls the ignition timing forward, sometimes by as much as 15 to 20 degrees. That means the spark fires earlier, giving the fuel mixture more time to burn completely. The result is better fuel economy, better throttle response, and a cooler running engine under cruise conditions. Old mechanics tuned this obsessively. They connected a timing light and revved the engine slowly, watching for the advance to come in at exactly the right moment. They adjusted spring tension inside the distributor, swapped advance canisters for different vacuum curves, and sometimes drilled out portholes slightly to change sensitivity. The genius is that this system delivers essentially free horsepower. You're not adding parts. You're just getting more out of the combustion event already happening. Modern fuel injection handles this electronically, but the principle is exactly the same. Number 18. Setting ignition timing by ear. This one sounds like black magic until you understand what you're listening for. Old mechanics could set ignition timing without a timing light, without timing marks, and without any equipment whatsoever. All they needed was their ears and a stretch of open road. The technique relies on listening for spark knock, that rattling, metallic tapping sound under acceleration when ignition timing is too far advanced. The air and fuel mixture ignites before the piston reaches the top of its compression stroke, and you end up with two pressure waves colliding inside the cylinder. It sounds awful, and it is. Over time, it destroys pistons, rings, and bearings. The old method was elegantly simple. Advance the timing until you just barely hear pinging under hard acceleration, then back it off until the pinging disappears completely. That's your optimal timing for the fuel octane you're running. You're finding the edge of detonation and sitting just below it. Experienced mechanics could do this in about 5 minutes. Drive up a hill, listen carefully, make a small adjustment with a wrench, drive again. Fast, surprisingly accurate, and required nothing more than a willingness to pay close attention. Number 17. Recurving the distributor. If you wanted a quick boost in throttle response from a stock engine without spending much money, old mechanics knew exactly where to look. The distributor advance curve, specifically the mechanical advance springs and weights inside the distributor that controlled how quickly timing advanced as engine speed increased. From the factory, most distributors were set up conservatively. Manufacturers had to account for poor fuel quality, high altitude, and hot weather. So the advance came in slowly and topped out at a moderate level. For the average driver, fine. For anyone who wanted more, it left significant performance sitting on the table. Recurving meant pulling the distributor apart, replacing the advance springs with lighter ones, and sometimes modifying the advance plate to allow more total mechanical advance. Lighter springs let the advance come in at lower engine speeds, which made the engine feel far more responsive from a rolling start. The process cost almost nothing if you did it yourself and took maybe 2 hours on a Saturday afternoon. A properly recurved distributor could feel like adding 30 or 40 horsepower even though no additional parts were installed. Pure tuning skill. Number 16. Points gap and dwell angle mastery. Before electronic ignition became standard in the late 1970s, every gasoline engine used a set of mechanical contact points inside the distributor to trigger the ignition coil. The gap you set on those points determined everything about how the engine fired. Most owners knew you were supposed to check the points gap during a tune-up. What they didn't know was the relationship between points gap and dwell angle, and how that relationship affected ignition timing and coil saturation. Old mechanics understood this deeply and used it to their advantage. A smaller points gap meant the points stayed closed longer during each distributor rotation. That's a larger dwell angle. Larger dwell meant the ignition coil had more time to fully charge, what's called full magnetic saturation, producing a stronger, hotter spark. Ideal for a performance engine with high compression that needed a powerful spark to light the mixture correctly. A slightly larger gap reduced dwell and reduced the load on the points themselves, extending their service life in high-mileage engines. By simply changing the points gap, old mechanics could tune the system for either maximum spark energy or maximum longevity. 2 effects with 1 small adjustment. Number 15. Carburetor float level adjustment. The carburetor float is a small component that most people ignore completely until the engine starts acting up. Old mechanics considered float level adjustment one of the most fundamental tuning steps on any carbureted engine. Get it wrong, and nothing else you do to that carburetor will matter. The float sits inside the carburetor bowl and regulates how much fuel is present at any given time. Think of it like the float in a toilet tank. When fuel drops below a set level, a needle valve opens and lets more in. When it reaches the correct level, the valve closes. Simple in theory, critical in practice. Set the float too high and the carburetor floods, fuel spills into the intake manifold, and you end up running rich, fouling plugs, and potentially hydro-locking the engine at startup. Set it too low, and the carburetor starves under load, especially during hard cornering or heavy acceleration. The engine stumbles or cuts out completely at exactly the wrong moment. Old mechanics checked and adjusted float level every single time they rebuilt a carburetor. They knew that a ½ millimeter off in either direction could mean the difference between a perfectly running engine and one that drove you absolutely crazy trying to diagnose. Number 14. Fuel mixture. Screw tuning. Almost every carburetor ever made has at least one small screw on the outside that controls the fuel-to-air mixture at idle. Modern mechanics often ignore these entirely or set them to factory spec and call it done. Old mechanics treated them like a fine instrument that needed to be played, not merely positioned. The technique was methodical. Start the engine and let it fully warm up, not partially warm, fully warm. Cold engine readings are useless here. Then connect a tachometer and find the highest idle speed by slowly adjusting the mixture screw in small increments. As the mixture approaches the ideal ratio, idle speed climbs. When it starts to drop again, you've gone too far. Back it off to the peak, then reduce idle speed with the throttle stop screw. Old mechanics went further. They'd lean the mixture until the engine just started to stumble, note that position, richen it slightly, and mark the screw for reference. In cold climates, they adjusted seasonally. Summer called for a leaner mixture, winter, slightly richer. It took maybe 15 minutes, and the difference in throttle response and fuel economy was immediately noticeable every single time. Number 13. Valve lash. Cold setting tricks. Valve lash, also known as valve clearance, is the small gap between the rocker arm and the valve stem on engines with mechanical lifters. Get this wrong and you get noisy valves, reduced performance, or in serious cases, burnt valves that require a full head job to fix. Old mechanics had specific tricks for getting this right that went well beyond just following the specification chart. The standard approach is to adjust valve lash with the engine fully warmed up to operating temperature. But old mechanics knew you could set valve lash cold, and they had a calculated method to do it accurately. They understood the thermal expansion rate of the engine materials and would add a few thousandths of an inch to the cold specification to compensate. So instead of setting hot lash at 12 thousandths on the intake, they'd set it to 14 or 15 thousandths cold, knowing the metal would contract to exactly the right spec once warm. No wrestling with a hot engine, no oil splashing everywhere. The bonus trick was checking lash while slowly rocking the engine by hand. If a valve was slow to return fully, it indicated a weak spring, a worn guide, or early signs of a bent valve, catching potential failures weeks before they became expensive problems. Number 12. The wet and dry compression test. A compression test tells you how well an engine's cylinders are sealed. Every mechanic knows that. But old mechanics used a two-step version, wet and dry, that turned a basic measurement into a precise diagnostic tool capable of telling you exactly what was causing the compression loss. The dry test comes first. Pull all the spark plugs, disable the ignition, hold the throttle wide open, and crank the engine while reading the pressure in each cylinder. A healthy engine typically shows consistent readings within about 10% of each other. Any cylinder reading significantly lower flags a problem immediately. Then comes the wet test. For any cylinder that failed the dry test, inject about a teaspoon of motor oil through the spark plug hole, then immediately retest. The oil temporarily seals the piston rings. If compression jumps up significantly after adding oil, the rings are worn. Internal engine problem. If compression stays the same or barely improves, the rings are fine but the valves are leaking. Burnt valve, bent valve, or a valve seat not sealing correctly. Head work needed. 2 tests. Definitive answer. No guessing, no expensive teardown until you know precisely what you're dealing with. Number 11. The exhaust color reading method. In the era of carbureted engines, old mechanics could diagnose a remarkable range of engine problems just by looking at the color and character of exhaust smoke. Quick, free, and in the right hands. Remarkably accurate. Black smoke meant a rich mixture. Too much fuel, not enough air. Could be a stuck choke, a leaking fuel pressure regulator, a flooding carburetor, or a clogged air filter. Usually a simple, inexpensive fix if caught early. Blue smoke was more serious. That's oil burning inside the combustion chamber. Blue smoke on startup that clears up quickly pointed to valve stem seals. Blue smoke under load pointed to worn piston rings or cylinder walls. Different pattern, different diagnosis, very different repair bill. White smoke in cold weather is just condensation, completely normal. But persistent white smoke after the engine is fully warm was a red flag for coolant entering the combustion chamber, head gasket failure, or a cracked head. Ignore it and you'd be pulling the engine within a few thousand miles. Old mechanics also checked exhaust smell. A sweet smell suggested coolant. An oily, acrid smell confirmed oil burning. They built a complete picture with nothing more than their eyes and nose. Number 10. Heat riser valve optimization. Here's one that almost nobody talks about anymore because most people have no idea what a heat riser valve is. On many V8 engines from the 1950s through the 1980s, there was a small thermostatic valve in the exhaust manifold called the heat riser. Understanding it was central to cold start tuning. When the engine was cold, this valve closed partially, routing hot exhaust gases through a passage in the intake manifold directly beneath the carburetor. The heat helped vaporize fuel more efficiently during warm-up and prevented stumbling on cold mornings. Once the engine reached operating temperature, a thermostatic spring opened the valve back up to let exhaust flow freely. The problem was these valves stuck constantly, usually stuck closed on older engines, which meant the intake manifold was getting cooked even when fully warm. The result was fuel vaporizing too aggressively in hot weather, a condition called hot fuel percolation, making warm engine restarts extremely difficult. Old mechanics checked this valve every single tune-up. They'd tap it gently with a hammer to free it if stuck, lubricate the shaft with penetrating oil, and replace the thermostatic spring if weak. 2 minutes of attention prevented dozens of mysterious drivability complaints. Number 9. Manifold heat crossover. Tricks. Building on the heat riser concept, old mechanics also understood how to control and optimize the manifold heat crossover passage. This is an internal channel cast into many intake manifolds that routes exhaust heat from one side of the engine directly under the carburetor mounting pad, a piece of engine design that most people today have never heard of. The factory crossover was designed as a compromise, enough heat to help cold starts, but not so much that it caused vapor lock on hot days. Old mechanics knew that depending on climate and application, the factory compromise wasn't always right. In colder climates, mechanics left the crossover fully open, giving maximum warm-up efficiency during winter. In hot climates, particularly on performance applications where heat soak was already a problem, they would plate off the crossover passage entirely, using a thin steel plate cut to fit between the carburetor and the intake manifold. This blocked the exhaust heat completely, kept fuel cooler under the carburetor, and dramatically reduced hot restart problems after a heat soak. On performance engines in summer, this one modification could eliminate the 10 to 15 minute wait after parking that plagued many muscle cars of that era. Number 8. Carburetor icing prevention. Most modern drivers have never experienced carburetor icing and have no idea it's even possible. But for mechanics working in cool, humid climates during the 1960s and 70s, it was a real problem that could stall an engine without any warning whatsoever. Here's what happens. When air rushes through the carburetor venturi, it drops in temperature due to the Bernoulli effect. The fuel evaporating into that airstream drops temperature further. In humid conditions with ambient temperatures between about 35 and 50 degrees Fahrenheit, roughly 2 to 10 degrees Celsius, this temperature drop can freeze moisture out of the air, forming ice directly on the throttle plate and venturi walls. The engine stumbles, stalls, and refuses to restart until the ice melts. Old mechanics knew exactly how to prevent this. First, they ensured the heat riser valve was working properly, because warm air intake helped prevent icing. Second, they routed the air cleaner snorkel to draw from near the exhaust manifold during cold weather. Many air cleaners had a thermostatic flap that switched between hot and cold air sources automatically. Third, on engines prone to icing, they added a small amount of isopropyl alcohol to the fuel tank in cold weather, which lowered the freezing point of moisture in the intake system. Simple, effective, and completely forgotten today. Number 7. Fuel pressure testing. Without a gauge. In a well-equipped shop today, checking fuel pressure takes about 30 seconds with a quality gauge set. But old mechanics often diagnosed fuel delivery problems without any gauge at all, using techniques so simple they almost seem too basic to work. They work. The most classic method was testing a mechanical fuel pump directly. Disconnect the fuel line from the carburetor, place the open end into a clean glass jar, and crank the engine for a few seconds. A healthy mechanical pump should deliver about a pint of fuel in roughly 30 seconds of cranking. Strong, steady pulse with each crank revolution. Weak, intermittent, or no flow meant the pump was failing. Old mechanics also tested pump pressure by feel. With the engine running, they'd momentarily pinch the flexible section of the fuel line between the pump and carburetor and quickly release it. A healthy pump sent a strong, sharp surge of fuel the moment you released the pinch. A weak pump produced only a mild, sluggish response. For vapor lock diagnosis, where fuel boiling in the lines caused a no-start condition when hot, they'd wrap the fuel lines with wet rags to cool the fuel and try to start. If it fired right up, vapor lock confirmed. Reroute the fuel line away from heat sources, problem permanently solved. Number 6. Air cleaner flow restriction tricks. The air cleaner on a carbureted engine is not just a filter. It's a tuned component that affects how the engine breathes, what temperatures the incoming air reaches, and how the carburetor responds. Old mechanics understood this intimately. Most people treated it as an afterthought. First, there was filter restriction. A clogged air filter doesn't just reduce airflow slightly. It changes the pressure drop across the carburetor and enriches the mixture, because carburetor metering is calibrated for a specific air pressure differential. Old mechanics tested filter restriction by holding a white cloth over the top of the air cleaner while briefly accelerating the engine. If the cloth stayed clean, airflow was good. If it turned gray immediately, the filter was saturated and restricting badly. Second, old mechanics paid close attention to air cleaner lid clearance. Many performance engines benefited from removing the air cleaner lid entirely or drilling additional holes, allowing the carburetor to breathe more freely at high RPM. Third, they used the air cleaner as a seasonal tuning device, directing warm air from near the exhaust manifold to the carburetor inlet through factory heat stove ducting, improved cold start enrichment, and reduced the need for an overly rich choke calibration. Small change, big real-world difference. Number 5. Cylinder balance testing by touch. Long before 4-gas analyzers and computerized cylinder contribution tests, old mechanics could identify a misfiring or weak cylinder with nothing but their bare hands and a few minutes of patience. The technique is called a cylinder balance test, and it is elegantly simple. With the engine running at a fast idle, you place your bare hand carefully near each exhaust manifold port, not on it, near it. A cylinder firing properly produces a consistently hot, pulsing manifold runner. A cylinder that's misfiring or not contributing runs noticeably cooler than the surrounding runners. The more controlled method was to disconnect the spark plug wire from each cylinder one at a time while the engine was running. When you pull a wire from a healthy contributing cylinder, the engine immediately drops in RPM and smoothness. It stumbles noticeably. When you pull the wire from a dead cylinder, the engine barely responds because that cylinder wasn't contributing much anyway. Old mechanics could run through all 8 cylinders in under 3 minutes using this method. They'd identify the dead cylinder, then systematically determine whether the problem was ignition, fuel, or compression. The original quick diagnostic tree. Cost nothing, and it was surprisingly accurate every time. Number 4. The propane vacuum leak method. Ask a modern technician how they find a vacuum leak, and they'll reach for a smoke machine, a specialized tool that pressurizes the intake system with smoke, so leaks become visible. It works well. It also costs several $1,000s. Old mechanics found vacuum leaks with an unlit propane torch and a steady hand, and their method was just as effective. With the engine running and idling, you'd slowly pass the propane torch nozzle around all potential leak points. Intake manifold gaskets, carburetor base gasket, vacuum hose connections, brake booster line, any area where a crack or gap could allow unmetered air into the intake. When propane vapor reached an active vacuum leak, the engine would suck it in immediately. The propane is combustible, and the engine would react, either smoothing out noticeably if the vacuum leak was causing a lean condition, or stumbling briefly as the extra fuel upset the mixture. Either response pinpointed the leak location exactly. It required a careful, methodical approach and a solid understanding of intake system layout. Done properly, it was fast, free, and absolutely definitive. Old mechanics used it without hesitation. Number 3. Multi-carburetor throttle synchronization. Engines equipped with multiple carburetors, think of the legendary triple two-barrel setups on the 1960 Pontiac GTO or the dual quad configurations on Chrysler's Hemi engines, were among the most exciting and most infuriating machines to tune properly. Getting multiple carburetors to open simultaneously and respond identically to throttle input required patience and precision that separated competent mechanics from truly gifted ones. The old technique relied on a simple tool called a vacuum synchronizer, or in some cases, just a length of small diameter rubber hose used as a makeshift stethoscope. You'd hold one end to your ear and position the other near each carburetor throat opening at idle. The sound, a low hiss of air rushing past, told you which carburetor was drawing more air than the others. The goal was a perfectly equal hiss at every throat. Throttle linkage geometry was then adjusted carefully, ensuring each carburetor's throttle blade opened at exactly the same rate and angle. Even a few degrees of difference caused one carburetor to run lean while another ran rich. Old mechanics who mastered multi-carburetor tuning were genuinely revered. Engines tuned correctly with multiple carburetors felt extraordinarily smooth and delivered a rush of power that modern fuel injection struggles to replicate. Number 2, oil pressure reading tricks. The oil pressure gauge on a classic dashboard looks like a simple readout. Good pressure, engine fine. Bad pressure, engine dying. Old mechanics used it as a precision diagnostic instrument that could reveal a surprising range of internal engine conditions no other external measurement could detect. First, they paid close attention to startup pressure. A healthy engine should show oil pressure almost immediately after cranking, within 1 or 2 seconds. Extended cranking with no pressure reading meant the oil pump was losing prime or passages were draining back. Old mechanics would pre-prime the oil system by cranking with the distributor removed, allowing the pump to fill all passages before first firing. This habit extended the life of hundreds of freshly built engines. Second, they watched pressure behavior as the engine warmed up. Pressure should be high when cold and oil is thick. As the engine warms, pressure drops, but should stabilize at a healthy level. Pressure dropping too low when warm indicated worn main or rod bearings, allowing oil to escape too quickly. Third, they watched pressure at idle versus cruise RPM. Healthy bearings produce a meaningful pressure rise with increased engine speed. Pressure that barely changes from idle to cruise pointed clearly to excessively worn clearances throughout. Number 1, timing light advance curve analysis. And here it is, the number 1 genius hack that separated truly exceptional old mechanics from everyone else. Not just using a timing light to set base timing, that's basic. Using a timing light to read and analyze the complete mechanical advance curve of a distributor, then comparing it against the ideal curve for the specific engine, fuel, and application. This is where real engine tuning happened. The technique involved a dial-back timing light, a type with a built-in advance dial that made the timing mark appear to stand still at any engine RPM. By slowly increasing RPM from idle to about 4,500 revolutions per minute and recording the timing mark position at regular intervals, the mechanic could plot the actual advance curve the distributor was producing in real time. Compare that plotted curve against the ideal specification for the engine, and differences were immediately visible. Advance coming in too early at low RPM caused pinging under light loads. Too late at higher RPM left power on the table. Maximum advance too high burned pistons. Too low, and the engine felt flat and completely uninspiring. Old mechanics used this method to optimize every distributor they touched, dialing in each engine individually based on its own specific characteristics. The result was an engine running at its absolute peak potential. No computer, no software, just knowledge, a timing light, and hard-earned experience. And there you have it, 20 genius engine tuning hacks that old mechanics used to keep engines running at their absolute best. These techniques took decades to develop and almost no time to disappear. Know any tricks we missed? Drop them in the comments. We'd love to hear from the old guard. Hit like, subscribe, and tap the notification bell. We'll see you in the next one.